Okay, we'll go ahead and get started. Your exam 0 grade exams have been graded, and you can see the scores in zip grade. So if you did all those bonus things, you log in, you see your posted assignments, and then click on, there's like a little green or white icon you can click on to see a photo of your exam, what you got right, what you got wrong, and your score. I will move those scores over into Canvas. When I get the time and motivation to do so, it's always a pain to do that. But you can see the points in zip grade. Please download the Excel file so that you can track your points and kind of see where your grade is going based on the available required course points up into this time. So you have another exam on Module 1 that will be Wednesday. I think there's no class Monday, right? So we have today and Wednesday to finish up Module 1. I think we're pretty good with the timing on that based on the number of slides left. So again, that will be the same format, 30 questions, multiple choice, A, B, C, and D. And that'll be open for 24 hours, so please make sure that you, again, don't forget about it. Please log in and do it. And I guess my advice at this point in time is to practice, and do some more practice. So how do you do that? Really, the best way to learn this is to do problems. So I don't really recommend as your main study strategy to just start reading the textbook. You actually have to be doing problems and writing stuff down, so solving problems. So go to your e-text, go to the end of chapter 1, pick out some problems, just start doing them. And as you go through that process, you might encounter a term that you don't know, then you can go read about it. When you do the problems first, you have a context of what's important. If you're reading, you're not really engaged so much. So when you're doing the problems, you're engaged. And as you do that, make sure you draw. I know the textbook's on the computer or laptop or phone, but if you have a tablet, like draw, or just do they make Mead spiral notebooks anymore? You know what I'm talking about? Paper. So buy a 99-cent notebook with a pencil and just draw some stuff out. As you're doing that, use your model kits to make and build models as well. So you get an idea of the shapes as we'll talk about today. This might sound hokey to you, but I think there is a firm connection between like drawing these structures like with your own hand and understanding them visually. So if you can draw a perfect hexagon, you'll know what cyclohexane is, and then when you build the model of that, you'll understand, okay, based on hybridization, which we'll talk about today, it's not flat. So we draw flat things, but when you build the model, you get an idea of the shape. And so that's really important to understanding the evolution of this material. So there's a lot. So you don't want to be drinking from the fire hose, as they say. You want to eat it in little bits so that you don't get overwhelmed. When you get overwhelmed, you get disengaged. When you're disengaged, you don't learn. And then you start hating me and you start hating life. And that's the butterfly effect, right? So any questions, again, about the course mechanics or exams, points, grades? Okay, so we had left off with the introduction of the hydrocarbon functional groups. Alkanes, alkenes and alkynes, and the name is telling us what functional group is present. So alkenes, and I want to clarify one thing. I'm sort of talking globally about molecules, but locally as well. So when we say an alkane, that means the carbon atom has 4 sigma bonds. When we say an alkene, there's a carbon-carbon double bond, but the molecule itself is not all double bonds. There's a double bond in there. The rest of the carbons can be kind of whatever. And then alkynes have a triple bond. So if you can visualize again in your mind an alkane, an alkene, and an alkyne, you'll see that the carbon, they all have 4 bonds, but they're different situations of those bonds. And we need to now sort of drill down in from what do those lines mean when we draw something. And if carbon, the letter C on the periodic table, is carbon, why can it bond differently? So from the 3 hydrocarbon functional groups, they show 3 different bonding patterns. But carbon is still carbon, so how can it do that? So as a review, we'll talk a little bit about orbitals, and this is very qualitative. The pictures you see on the screen, those are derived from mathematical equations, like pretty complex equations. And to be completely honest, I don't understand them. They're pretty long equations. Does anyone know the name Schrodinger? So that's one of the principal physicists / mathematicians that came up with this stuff that results in those orbitals. We want to think of the orbitals kind of as shapes, but with the understanding, the limitation of like what you see. So it says shapes of s and p orbitals. And you see here on the screen, there's like the white background of the slide. So you're walking along and then you hit this blue color. That's like a boundary. And then, yeah, that resembles a sphere. So we're not flat orbital people here. We're it's Earth is a sphere. The orbitals have 3 dimensions, sort of thing. So it looks like you're running into a boundary, like a hard boundary. From here to there, you're stepping into it. But orbitals are really, you want to think of them like clouds. So like if you've been in an airplane, you're looking out the window, like we're coming into some clouds. It's a gradual transition. And what the color is representing is the probability of finding an electron. So the further you get away from the nucleus, and then depending on the shape of the orbital, that probability will change. So like if we could, although we can't, but imagine we can, see an electron. Is it a particle? Is it a wave? What is it? But if you were here, you wouldn't see anything because the probability of that electron being in that region of space is very low. But the blue boundary it's higher. So that's an s orbital. S orbitals are spherical. And then these are p orbitals. They're the dumbbell shape. The color is different. Don't think of that too much as binary in terms of like something's changing. It's related to the sign of the mathematical function, so like a phase. So it has this lobe above and below, sort of, we're on these different axes. So the three-dimensional coordinate system, so X, Y, and Z. This one happens to lie on the Y-axis. The other thing I want to point out, this is not a cylinder. So there's a lobe shape, and then right where all three axes meet, there's nothing. So the lobes don't touch there, and that's called a node. A node just means there's zero probability of finding the electron density there. And so that's all stuff from Gen Chem. You learned about, how atomic orbitals are filled with electrons and why they have these shapes, the number of nodes, that kind of thing. So we're really just concerned with, again, period 2 with carbon, so the 2s orbital, and then there's 3 of these p orbitals in that period 2. And one thing I want to point out is that the p orbitals are all degenerate. That in our context, it doesn't mean like a bad person or something. It just means kind of equal energy. So we reviewed all this stuff, and you can accept it as fact, and maybe it's simple, but we want to think a little bit deeper about what it's telling us and why it kind of fails. So we said carbon was atomic number 6, and that was the number of electrons we have to work with. And so when we're filling these atomic orbitals, we go period 1 first, that's the 1s, so there's 2 electrons, they end up being spin paired. Now we get into the next period 2. The next orbital that's encountered is the 2s orbital. We spin pair those. And then we have the 2 remaining electrons. And this says 2p2. And what was the rule of filling atomic orbitals? So you can't spin pair them if there's degenerate orbitals. So they have to go in these sort of one by one before you go back and start spin pairing them. So we already know from our discussion in communicating structure that carbon forms 4 bonds. So we can put a break there and call these our core electrons. So we don't consider them, they're not important for just what we need to do. So the 2s2 and the 2p2 are used for bonding. And so I'm going to throw a question out there. What is the problem with that? Just based on what we just said about filling orbitals. What? Yeah, so that's a practical implication of it.
Not all of the degenerate orbital shells are filled.
So when we're plugging these electrons in here, the 2s2, those are spin paired. So what does that mean in terms of a bond? If they're spin paired, they can't bond. They're not available for bonding. So in the 2p2, you only have 2 electrons that are not spin paired, so the consequence would be I could only form 2 bonds. Then the other thing gets back to the disposition in space of these orbitals, as the student said about the bond angles. Say the 4 valence electrons were not spin paired, and you could use them in bonding. Well, look at these orbitals. The s orbital, again, that's a sphere. So I want to say kind of 2 things at once, but I can't. So these are the electrons in here are in a sphere. And then these 2 are on different axes. And as we'll find by looking at alkanes, alkenes, and alkynes, there are certain bond angles that are observed in those functional groups. And let's just consider the y-axis here and this x-axis. So based on the Cartesian coordinate, they're at a 90-degree angle, right? So if you had something coming in, another thing coming in, the bond angle would be 90. And again, we can't know things in a linear order, so we have to do this, again, recursion of things. So that is a problem. Alkanes, alkenes, and alkynes don't have 90-degree bond angles. So while the atomic orbital is useful for counting electrons, they do not accurately describe what we observe in molecules. But that's all we have to work with, are atomic orbitals. And orbitals in general are weird. I can look at a picture and say I kind of understand that, but I kind of don't as well. So this is from a textbook. Whether it's yours or not, I do not know. I don't remember. So the nucleus is in here. The little blue thing here, that's the 1s orbital, that's a sphere. Then the 2s orbital is this greenish looking thing, and then the 3s, those are the spheres. And then you have the p orbitals. Where are they in space? They're like all overlapping one another, right? But within those different orbital energy levels, that's the probability of finding those electrons. So the fact that they're all kind of here in different angles isn't good for us in describing the molecular reality. So as I mentioned, when you're doing problems in your drawing stuff, again, the drawings are flat, but you really want to start building models and thinking in 3D, because that has implications about things we'll learn in the subsequent modules with how do molecules move, what are the, I'll say, symmetry operators, how does that affect the conformation, the shape, how does that affect the reactivity? So here's our three-dimensional Cartesian coordinate x, y, and z. And I've just overlaid that on here. And we're going to think about how we can do something to those atomic orbitals that will better describe molecular orbitals. So again, the issue was of the 4 valence electrons, 2 are spin paired. We have 2 that are not. And then the atomic orbitals are in different axes and things. So what these physicists did, like Schrodinger, Einstein, Dirac, Heisenberg, all these people, they did a lot of math. And so in this term, we just say hybridization. So in math, there's different functions and operations you can do with equations, and the outcome of that are these molecular bonding orbitals that we can use that better describe things. So the hybrid orbitals that we are interested in are sp3, sp2, and sp. And that nomenclature just tracks from the s and the p atomic orbitals. So notice here with sp3, if you count the total number of orbitals, how many is there? 4. There's the s orbital and then 3 of the p. That equals 4. What about this? How many are there? There's 3, so there's 1 missing, right? And then for sp, I think I had a mistake there, so that should be sp. There's just 2, and so there's 2 things missing. So that's leading us down this qualitative descriptor of these hybrid orbitals. So here's a more visual representation of that. On the left, there's the atomic electron configuration of carbon. This red arrow is energy. And so we fill these orbitals from the 1s. So we put an electron in, we spin pair it, it's full. We then move up to the next period, the next shell, that's the 2s, another pair of electrons. And then for the degenerate p orbitals, again, they have to go in unpaired. So all we're doing is looking at these 2 levels here. And again, there's a lot of math, but qualitatively, we're just going to mix these things in different proportions. And those proportions then describe the type of carbon we see in the different functional groups. One thing I do want to point out, so the distance between here, that's a change in energy. So when we take the s orbital and then these 3 p orbitals and mix them, notice where the energy ends up. It's in the middle. It's not lower, it's not higher. So I have this 2 in front. That just means it's period 2. So let's be clear on that. So when we mix those, now we have 4 degenerate hybrid orbitals. And then we started with the 4 valence electrons. Now we can just fill them in and they're unpaired. So that means we can use them in bonding. All 4 of them are free to bond. And so the molecule that's shown, this is ethane. And then we would say each carbon then is sp3 hybridized. And visually, another way of recognizing that is just counting. So there's the carbon. We have 1, 2, 3, 4 single bonds. We also call them sigma bonds. So sp3 has 4 sigma bonds. We said with sp2, there were 3 total orbitals. And then we had that thing remaining. So the thing remaining is a p orbital that we did not use. Notice that it's at the same energy of the p orbital we started with. So we have 1, 2, 3 sp2 hybrid orbitals, and then this remaining p orbital. So this was ethene. So those are both sp2. And then if we count, we have 3 sigma and 1 pi. So that gets us our 4 total. The Carbon is always going to have 4 bonds. What combination of them is based on the hybridization? And then lastly, we have ethyne. So that's sp. We took one of the s's, one of the p's. We have 2 of these degenerate orbitals and then 2 remaining p orbitals. So this has 2 sigma and 2 pi. That's the 4 total bonds to carbon. So again, when you look at a molecule, you're going to classify in a lot of different ways. If you're given a structure, you can count the carbons, the hydrogens, all the other elements. That's the molecular formula. You can determine the molecular weight from that. Now what you can start doing is looking at each carbon, what is the hybridization? And you do that visually, by counting, by counting the bonds. Is it a single bond? How many are there? Are there pi bonds? You count them, they got to equal 4, and then you can classify them that way. This other last thing on the slide says %S character. And that's important when we start talking about acidity and acid-base chemistry. The number is basically derived from basically a 1 on top. So there's just 1 s orbital that's used. And then the total number of orbitals, so there was 4. So that equals 25. And then this equals 1 over 3, and that's 1 over 2. So the hybridization, we can talk about %S character, and we'll dive more into that with Module 3. Any questions at this point? So what are the implications of that hybridization process? So it impacts the shape of that carbon. So for an alkane with sp3 hybridized carbon, you have 4 sigma bonds. And if you like 3-dimensional geometry, if you're at a point, like you're sitting at a point, and then there's 4 other things around you, like what's the best arrangement of those 4 other things to maximize their distance from each other? That ends up being this, which is called a tetrahedron. So you have 1, 2, 3, 4. So a tetrahedron means those points relative to the center, no one point is closer than the other. It's just mathematically falls out that way. So we would say an sp3 hybridized carbon is tetrahedral. And this like circus balloon dog looking thing, it's showing you sort of the sp3 hybrid orbital, then the hydrogen, and then they form that bond. For an sp2 hybridized carbon, we said there were 3 degenerate hybrid orbitals, and they're shown in gray here. This red-blue thing, that was the empty p orbital. Well, not empty in a sense. It has that electron we're going to use for bonding. But notice the arrangement of the gray orbitals. They are all now in a plane. So say they're in the x plane. the p orbital is 90 degrees from that. So in an alkene, we have the two sp2 hybridized carbons. They form a central sigma bond. Then you have a p orbital with an electron, a p orbital with electron. 2 electrons make the pi bond. And so then this is what, again, is a little screwy about this. If you're only thinking of those electrons as particles, there's overlap here in the red and the blue. And then remember we said there was a node? There's no electron density of the pi bond along the sigma bond axis. So it's imagine like you have a hamburger with like the buns, but then there's nothing in between. So it's kind of not satisfying, right? But the pi bond are these clouds above and below. Like in between, there's nothing. For an alkyne with a triple bond, so we have a single bond, a double bond, a triple bond, there's now 2 pi bonds. So we have a central sigma bond, p orbitals on one axis, and then 90 degrees from that, p orbitals on the other. So what is the take-home message? Again, I'm not going to ask you to derive the Schrodinger equation from first principles. You're counting the lines. So again, the lines are bonds. That's a sigma bond. Now you have a sigma plus pi. That's a double bond. And then sigma plus 2 pi. So you count those, you classify it. That'll spit out what hybridization it is. So going back, I want to just write this stuff down here. So tetrahedral. Trigonal planar. And then the SP was linear. So on the slide, you can see some models. Those are kind of tiny plastic models, but I've brought in these big ones. So this should look like your kit if you did the selfie thing. It's just a bigger version of it. So what hybridization of carbon am I holding? So sp3. So visually, you're seeing 1, 2, 3, 4 single or sigma bonds. And then, as I said, if you know you're sitting here, you have these 4 different points, and so the ultimate shape of that is called a tetrahedron. So I don't want to get too much into the geometry or anything, but you can only have like 3 of them in a plane at any one time. And so these planes have different faces, and ultimately that gives that shape. And then now this is what functional group? Alkene. So the carbon is in there. I swear it's connected. So let's think of the yellow ones as hydrogen. So that's a sigma bond. That's a sigma bond, and then I'm holding the 3rd one. So that's sp2, and then this is the representation of a p orbital overlapping with the other p orbital. So notice that the 3 sigma bonds are all in a plane. So 3, that's the trigonal, and then they're planar. And then of this plane, the p orbital is 90 degrees from that. And so this is your sandwich bun in the bun, and then between here is the node of that pi bond. And now this is the alkyne. Notice when you're looking directly down the carbon-carbon bond axis, sort of the colors, you know, if the blue-green is a p orbital, it's overlapping, say, in this y direction. So that's a pi bond. And then 90 degrees from that is the other set of p orbitals. So you have two pi bonds, you know, cloud here, cloud there, and then this cloud. So overall, the two pi bonds kind of make like a cylinder shape around the central sigma bond. And then this is linear. The other thing I want to mention as well, when you're drawing and building models, if you take like physics 2 or something and you start learning about like relativity, like what does that really mean? How do they come up with this stuff? You know, like frames of reference. So like when I hold this, I'm looking down this H to this carbon. So I see like an axis, but like what you see is this plane of 3. So don't get stuck up in one way of drawing something and looking at it, because the molecules like rotate, they tumble and stuff. So you have to understand that if I draw it the way that you're looking at it versus the way I'm looking at it, the drawing looks different, but the molecule is the same molecule. So again, I'm not an artist, I can't draw orbitals, so we represent the bonds as lines. But always keep in the back of your mind that those lines actually do have a physical meaning, the electron density, all that stuff. So here's a summary of the hydrocarbon functional groups. So I'll say FG for functional group. Again, the end of the name is telling you sort of the parent, or what's the main sort of bonding pattern present. This was the molecular formula. As we go from alkane to alkene, we're losing 2 hydrogens, and we defined that as a degree of unsaturation. So we lose another one. So the alkyne has 2 degrees of unsaturation. So from a structure to hybridization, you count the number of bonds till you get to 4. There's going to be some combination of them. Are there 4 sigma bonds? That would be sp3. What do I mean by free rotation? Isn't perhaps the best. I should have brought some more of these, but let's say these 3 are hydrogen, but then this one is another carbon. So imagine this over here. So in this hand, what I can do is I can rotate along that axis. It's free rotation, sort of asterisks. We'll learn it's not always that free. But now I have 2 carbons, and notice I try to rotate them. I can't. Like, I can't get this blue color down here. So a pi bond does not have free rotation. That's because the electron cloud is locking it into that place. And then the same thing for this as well. So bond length, you'll see this weird looking A with a little circle on it. That's called an angstrom. An angstrom is just defined as 10 to the minus 10 meters. And you'll notice that as you go from the alkane to the alkene to the alkyne, the distance between the carbons decreases. The reason for that is you're putting more electron density between them, so they're more attracted, the bond length contracts. The bond energy, we're going to use kilojoules for energy in this class. Your book may use calories or kilocalories or something. Kilojoules is the SI unit, so we're going to stick with that. Notice that the bond energy increases now. So a sigma bond is worth 347 kilojoules per mole. And then when you get up to the double bond, it's 612. So why is that? Well, you have all the energy from the sigma bond. You've put a second bond there, so this has to be higher. It's a stronger bond. And then the same thing happens for the triple bond. We talked about the geometry, tetrahedral, trigonal, planar, and linear. Let me just shove in some numbers here. So this was 4 and 0, 3 and 1, 2 and 2. And then the other column there, the bond angle. So again, some cheap geometry. Even though you're paying tuition for organic chemistry, I'll throw in a preview of some geometry here. So this is a point, and when I put it on here, from here to here, that's 2 points, that's a line. And now I have this third point. Now I can form an angle. So carbon, hydrogen, carbon, hydrogen. So three atoms need to be defined for an angle. For sp3, you want to memorize 109.5. So every HCH in this molecule is 109.5 because we said there was one uniqueness set right. For sp2, if we define the 3 points now, we have H, C, and C. They're in this plane. So the bond angle is now 1 point. So if you take like a circle and chop it in 3, you get 1 point. So anytime you bisect, a circle, so if you chop it in half, 180 plus 180 equals 360. Depending on the number of ways you're chopping it, it has to equal 360, right? And then finally, H, carbon, carbon, because this is linear, that's 180. So those are the 3 main bond angles you want to know. So as I said, I'm drawing stuff flat. We've made some toys here to look at. I posted these videos in Canvas by this page on YouTube called Sponholz. And he goes through all this, starting from the Gen Chem perspective up to organic, with some nice visualizations where they can overlay these orbitals and stuff, and you see their orientations in space. I will caution you though, the music is as trippy as the background in here, so it's a little weird in that sense, but if you're a visual learner, they're pretty nice to watch. And then this table summarizes, it says atomic geometry, but again, we're thinking about the hybrid orbitals of those atoms based on the types of bonds they have. So the green, I guess, sort of step-looking thing there, or those are the geometries that we'll cover in this class. The rows 5 and 6 here, that's mainly for transition metals that have d orbitals available to them, so they can get into these other shapes that you see. But tetrahedral, trigonal planar, linear, so those kind of the carbon stuff. And then these other ones, when you start shoving heteroatoms in there, even though things might look sort of tetrahedral or something, they have a different nomenclature because of lone pairs and things like that. So because lone pairs are not considered substituents or ligand on the element, that's why we don't say like water is tetrahedral. It only has 2 substituents, then 2 lone pairs, so it's bent. Even though there's sort of 4 things there. Does anyone work at CVS or Walgreens? Just bring me an IV bag so I don't have to keep drinking water up here. So what we'll do now is we're going to review the carbon H functional groups. Then we're going to move across period 2 and start putting in these other elements. And so the remainder of this module 1 here is what are the names and bonding patterns of these functional groups. So again, these are molecules with carbon only, and then we know that there's always hydrogen, so what are the patterns we're looking for? And then what's some other classification or nomenclature we have to be aware of? So we say alkanes are fully saturated. And that term in this case means that the carbon has 4 sigma bonds. To state it explicitly as well, there's no pi bonds. So we have 1, 2, 3, 4, 5 carbons. There's no pi bonds in there. So that's saturated. That's called pentane. And these numbers that I'm showing, we can go over to this table to the top right. And as I said, we're going to use a lot of numbers in different contexts in this class. So the red numbers are the counting the carbons along the chain. So if I look at carbon number 1, I see 1 explicit bond. So 4 minus 1 is 3. That carbon has 3 hydrogens. It's a CH3 group. That's called methyl. In terms of a number, it's then called primary. So that number and then the little degree sign. Carbon 2, I see 1 bond, 2 bonds, so 4 minus 2 is 2. That has 2 hydrogens. So that's called a methylene, and the carbon is secondary. So carbons 2, 3, and 4, those are all secondary, and then 5 is methyl primary. And then we made this, so here's a linear compound. And these are branched compounds. Again, branched just means as you're walking along the path, well, hey, I can take a different path. So in this numbering system, carbon 2 ends up being tertiary, and that's called methine, a CH group. So if we use some dots, how do we get tertiary? So let me say this is the carbon we're standing on, is the red dot. And then from there, we just count the total number of carbons bonded to it. So 1, 2, 3, that gets us tertiary. And then the last example of a branched, so carbon 2 has 1, 2, 3, 4, so that's called quaternary. So there's no attached hydrogens. And as I said in the prior lecture, we don't want to be, lemmings when we're doing the uniqueness test and always thinking that the unique number of carbons is going to have the same number of unique H sets. And this is the reason why sometimes it won't, because you'll have carbons with no hydrogens attached. So alkenes have a degree of unsaturation due to the pi bond. So underneath these, you see a little bit more sort of sub-classifications. This one's called terminal because the alkene is at the end of the longest chain. If you migrated that internal, so now it's internal, and then they have these other things associated with them. These are just nomenclature terms. And to explain what they mean, I'm going to draw the H's in. So in red, I've highlighted the sp2 hybridized carbons. Now, if we look at the things bonded to each, and what I mean by that is just the sigma bonded stuff. So this carbon has an H. So carbon has an H and a C. So does this one, C and H. These designations tell the relationship of the substituents. And so the way this is done, and I'll write this in blue because these are some different numbers here. What is the element? And then what's its atomic number? So hydrogen's 1. Carbon is 6. So those are atomic numbers. And then we're gonna do it up royal here. In green, I'm gonna write a priority. The higher the atomic number, the greater the priority. So 6 is gonna get the priority. So that's gonna be 1, and that will be 1. So relative to the double bond, what's the relationship between the highest priority? So here they're on opposite sides, so that's what trans means. And then organic chemists will further abbreviate that to E. So E it comes from a German word that starts with E. And it's telling you the relationship of those highest priority substituents. So when we look at the other one, so again, atomic numbers 6 and 6. So priority 1 and 1, they lie on the same side of the double bond. So that's cis or Z. So some other synonyms we can throw in here. Opposite and same.
How is that opposite?
So let's say, I'll do it in green because that was the numbers. So this is sort of you as the student standing on sort of one side of the double bond. So you see one of those numbers on that side, and then the other number is on the opposite side. So remember, again, the skills we need to develop are the 3D skills. So, like, in terms of our reference point, like, you are sitting on this side of the double bond. Remember, these can't rotate, right? So there's no rotation. So that's a side, and then I'm on a side. So there's a priority group here on this side, and then here on this side. So they're on opposite sides.
And you said those two red dots were SP or SP2?
SP2. So there are two types of alkynes. Terminal, again, that's at the end of the chain. So let me highlight those in blue. This is a carbon, and that is a carbon. So don't forget that H. So a terminal alkyne will always have an sp hybridized carbon H bond. The internal, you're just moving it inside. So again, the 2 degrees of unsaturation come from the 2 pi bonds. So now I'm going to say something that's maybe like paradoxical in a sense. You can have hydrocarbons that are rings. So imagine you take a chain and you tether the ends together, that makes a ring. A ring is a degree of unsaturation because to bond the ends together, you have to remove H2. That's a degree of unsaturation. But look at the way these are drawn. Each carbon atom has 4 sigma bonds. So the carbon itself is saturated, but the molecule has a degree of unsaturation. And then another class of carbon, hydrogen. Yeah, question?
Basically, even if there is no pi bonds, because it's a ring, it would always have 1 degree of unsaturation.
Right. So there's another special class that we'll talk more about in Organic 2 called aromatic compounds. And what does it mean to be aromatic? What do you think of? What? Hair gel? So you probably think of hair gel because it has like a smell to it that's kind of like a pheromone or something. So originally, the definition for these compounds came from the smell, like they have a unique smell. Chemically, aromatic means something different structurally. So an aromatic compound has to have a ring and then the pi bond unsaturation. So it's a combination of both. This molecule is called benzene. So there's one ring and 3 pi bonds, so 4 degrees of unsaturation. The next molecule is called naphthalene. Has anyone, you ever smelled benzene? A couple people? It's okay. It's, not the best smelling thing. I'm sure you've smelled naphthalene. Where have you probably smelled naphthalene? Yeah, you go over to Meemaw and Peepaw's house, and they have mothballs in the closet. It's not really a problem anymore, but mothballs, keep the moths away from eating fabric. Back in the day when those old crusty boomers were rich, and they could make their closets out of cedar wood. Cedar has oils in it that repelled moths as well, but if you weren't stacked, you had to buy the mothballs. So those are things we'll learn more so in organic too, because again, aromaticity has a structural definition, not just the smell. Any questions? So here again, is sort of the way that I think about organic, and you got a flavor of how I write the exams, and so it's going to be more of the same. Do you know these fundamental things? Here's a molecule that looks pretty complex, but if you start thinking about everything you can, for the most part, describe, a lot of the structural features. So the molecule is called gifratoxin, and then this is a harlequin poison dart frog. You ever see these things? How big are they, or how small are they? They're pretty tiny. I went to the aquarium in New Orleans a decade ago or something. They had an exhibit. I mean, they're really tiny, but they're crazy colorful. And so they don't produce this. You see this, he's or she is munching on this leaf. There's these fungi that live on the leaf that produce this stuff. The frog eats it. This molecule is secreted. And then the warrior comes along with his arrowhead, rubs it along the back, and now the arrowhead is poisoned and he can shoot his enemy. And so it's toxic to humans. But that's interesting to think about. Again, even if you don't like organic chemistry, if you're a biology major, from the cellular molecular level, up into this organism, why does a fungus make that? And then why does this frog eat that leaf in life? So in the molecule, there's a lot of stuff. And so I've highlighted carbon A and B. So looking at the bonding patterns, what are their hybridizations? So what do we think A is? So we can eliminate that and that. And then B is what hybridization? sp2, so we can eliminate that. So again, how do you eat an elephant, one bite at a time? When you approach questions on the exam, don't let some cortisol response freak you out and stress you out. I don't know what to do. Just apply these steps as you're looking at these things, and it's getting down to something very fundamental. So the next question is, how many sp3 hybridized carbon atoms are there? And, I'll give you a couple seconds to do some stuff, but I really want to point out a way of looking at molecules that I think is important, because your eyes see everything, right? I mean, you're seeing these lines and the colors, and you're taking it all in. So how do you slow down and logically answer this question? Well, number one, you want to start somewhere on a path. The path is the carbon backbone. So let's start there. It looks like we can walk right on there. So we're starting there. That's a carbon. That really doesn't look like it obeys the sp3 rule. We go there, that not so much, that and that. We kind of already know these four are not, because you need two of them to form a triple bond. You need two of them to form a double bond. And then we're going to walk along the backbone, and I'll change the color to blue here so we can count. When we step off the alkene, now we're here. So we're showing 2 bonds. So the other 2 are hydrogens. What the hell does that mean? So it's called a dash. It just means the carbon is sp3 hybridized. And we said that the geometry is tetrahedral. So say that the 2 hydrogens I'm holding are in this plane here, the plane of the whiteboard. Notice the other 2. This one is towards you. This one is away from you. So the dash means it's going back. The bolded wedge means it's projected towards you. So that was 1, and maybe I want to do this in another. I'm going to get fancy here. Hopefully I don't clash the colors. So I'll backtrack. We're going to start here, and I'll highlight in blue the path we want to take. So we want to take that path. So what you don't want to do is, hey, look at that one. Ooh, look at that. Oh, that looks nice. That's cool. You don't want to hop around, because then your mental computing capacity is going to get overloaded, and you're going to need a reboot. Yeah.
How would you represent forward and back leading stuff with double or triple bonds? How would that be?
So the question was if we needed to do that for a double bond, and say we could sort of draw that and then project these out like that, and then those are away, so you can.
I meant the wedge itself is the double.
Ooh, I don't know if we would do that. That would be a little faux pas. You'd probably want to move it in such a fashion that it's not doing that, because then it'll get a little bit harder to interpret. Maybe not. So let's continue on here in the blue pen here. So we said 1, then we're going here. That's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Did I count that right? So, I teach on the iPad here, and the app I'm using is called Explain Everything because it allows me to record these for screencasts, but I never really used a whole lot of color prior to, teaching on this thing, but I think it does help when you're sort of making your own color key and you're classifying things so that it's not sort of monotone and you make a better association of the different information you're trying to classify. So let's just, so so I guess what I mean by that, maybe we'll do these. So that's a way you can classify them. Then the next level of that is, okay, of each of those, how many are attached hydrogens? Can you classify those? Then you dig a little bit deeper and deeper. And I made a boo-boo here. So maybe on your slides, the 2 was down here, but I want it to be there. So you have these Roman numerals 1 and 2, and it says, what are the classification of the carbon atoms 1 and 2? So 1 has a carbon and a carbon attached to it. So that has to be secondary. And then carbon 2 here has 1, 2, 3, so that has to be tertiary. So that would kick that one out. And then we would be left with D. Any questions? So we got about 2 minutes. Maybe let me just blow through some slides, and then on Wednesday of next week, we'll go through things more slowly, but just to give you an idea, we're done with carbon. Now we're going to start putting nitrogen into the molecule. These make different functional groups, again, based on the degrees of unsaturation. Nitrogen's not too bad. Oxygen is where you're going to earn your money. So there's a lot of oxygen-containing functional groups. And again, a functional group is a discrete collection of elements with a specific bonding pattern. So like alcohol. Alcohols always have OH. Then we can put some unsaturation in here. That's something different. Then we can look at what else is in there. So there's probably about 15 or 20 functional group patterns you need to know. We'll talk about those, the unsaturation, all that stuff. And then we'll wrap up next Wednesday on the other things we need to know about, like resonance and formal charge. And then we'll know what we need to know to continue on with the rest of the semester.